So hello everyone, let us continue with the thermal radiation heat transfer. Okay, with the topic radiation heat transfer. Fine. So radiation heat transfer. Okay. In the last session, we were looking at the end of the last session, we were looking at the electromagnetic spectrum, right? So when we looked at the electromagnetic spectrum, we saw that the thermal radiation actually falls under a category that is from 10 to the power -1 to 100 micrometers, right? So 10 to the power -1 to 100 micrometers. So there is a wide range of wavelengths over which this thermal radiation actually falls. Okay, which means that the thermal radiation emitted by a surface is made of a range of wavelengths. Okay, and the magnitude of the radiation, and thus the magnitude of the radiation actually varies with the wavelength. Now that sort of behavior or that sort of nature is actually called as the spectral behavior or spectral nature. I'll just show you an image of that. So that is called as a spectral behavior. Okay, I'll just bring in the figure. See what is happening. Okay, so the spectral distribution is so it's given here. That is the you can look at the power of the monochromatic radiation emission. Okay, so that the value of or the magnitude of the radiation emission actually changes with respect to the wavelength, because the wavelength actually changes in this direction, and the monochromatic radiation emission, the strength of that will actually, magnitude of that is actually changing in this direction. So basically that depends on the wavelength. Okay, now along with the change of with respect to wavelength, for a particular wavelength, like say 0.1 micrometers or 100 micrometers or any value in between that, the magnitude of the electromagnetic radiation or the thermal radiation depends on the temperature and nature of the surface. Okay, so it not only depends on the wavelength. Now for a particular wavelength, it depends on the radiation depends on the magnitude of temperature and the nature of the emitting surface. Okay, now this kind of nature is called as the spectral distribution. Okay, then there is another type of distribution which is called as the along with the spectral distribution, the second feature of this radiative heat transfer is its directionality, which means that a surface can actually radiate heat in different directions. Okay, and the magnitude and direction of this monochromatic radiation actually depends on the direction. So the magnitude actually depends on the direction in which it is emitted. So as we discuss now, there are two different types or two different features on which the magnitude of the monochromatic emission or the radiation depends, and one is the wavelength. So the emission actually depends on the radiation actually depends on the wavelength, and the second one is it depends on the direction from which it is getting emitted. Okay, so the first one, the one that it depends on the wavelength, is called as the spectral distribution, and the second one is called as the directional distribution. Okay, so these are the two features of thermal radiation. Okay, now having said that, now we will slowly move on to the physical nature is already explained. Now after that we will move on to the different radiative heat fluxes. Okay, so radiative heat fluxes. Radiative heat fluxes, let me just write down that radiative heat fluxes. So Let us see the different types of radiative heat fluxes. First one is called as the emissive power, E. So emissive power, okay, E, and its unit is watts per meter square. So if I just bring in a figure, and with the help of a figure I hope we will be able to explain that. So okay, so the emissive power is given by, so you can see the emission here, right? Emission E is actually written here, this one. Okay, now the emissive power is the rate at which radiation is emitted from a surface, rate at which radiation is emitted from a surface per unit surface area, per unit surface area over all ranges of wavelength and in all directions. So here you can see that we have considered both the spectral nature and the directional nature, that is in all directions and all wavelengths. Okay, so the emissive power is the rate at which radiation is emitted from a surface per unit surface area over all wavelengths. So that itself is the unit, right? You can see that watts per meter square, that is per unit area. Okay, so that is the emissive power. We will discuss more about emissive power when we go through all the relations of emissive power and everything. But right now we'll just go through all the radiative heat fluxes. We'll just list down all the radiative heat fluxes, and I'll just give you an information about, just a basic information about what these things are. Okay, now the second heat flux associated with the radiation is the irradiation. Okay, it is called as irradiation. Okay, that is given by the letter G, watts per meter square. Okay, now that is the rate at which radiation is incident upon the surface. So radiation is incident upon the surface. Upon the surface per, once again, per unit surface area, and it is applicable for all wavelength and in all directions, over all wavelengths and in all directions. So if you look at the figure that is given above, so if you look at this figure, we can see that the irradiation, this is the irradiation, that is, so you have a surface here. We'll see what this is written as opaque medium. We'll see what opaque medium is after explaining this thing. So irradiation means you can see all the radiation coming in and hitting the surface. That is called as the irradiation per unit area. It's called as the irradiation, and whatever is emitted from the surface is actually emission. Okay, now there are two more radiative heat fluxes. One is called as the radiosity. So that is the radiosity, and the other one is net radiative heat flux. Okay, net radiative heat flux. Now before going to these two, and both of them are actually the unit is watts per meter square. Before going through these two radiosity, these two heat fluxes, radiosity and net radiative heat flux, we have to be familiarized with, or we will have to get familiarized with some another properties. One is called as the concepts. Okay, some other concepts of reflectivity, transmittivity and absorptivity. So after explaining what reflectivity, transmittivity and absorptivity is, we will come back to these radiosity and net radiative heat flux. Okay, now for explaining the radiative, transmittivity, reflectivity and absorptivity, we actually consider or classify objects into two different types of into two. Okay, one is the opaque objects. Okay, one is opaque object. Now opaque object is the object that actually doesn't allow any radiation to pass through it. Okay, it is not like a metal is an opaque object. A metal is not an opaque object because it will actually allow the radiation to pass through it. So opaque object is actually an object that doesn't allow any radiation to pass through it. Okay, so we'll see that. If you look at this picture, in this case no radiation is passing through the object, right? Here you don't see any radiations passing through this, whereas the second one is the semi-transparent medium or semi-transparent object or semi-transparent medium. Okay, in that case, now you can see the difference. In this case, see that for a semi-transparent medium, some part of the irradiation is actually transmitted. Okay, some is reflected, some is absorbed. Okay, now in the opaque object also there will be absorption, but mostly it is reflection and emission. Now in this case, in semi-transparent medium, there will be transmission also along with that. Okay, now we'll see transmission is there as part of the semi-transparent medium. Okay, now in the case of a semi-transparent medium, a part of the radiation will be reflected, a part will be absorbed and a part will be transmitted. Okay, so what is this radiation reflected, what is the radiation absorbed, what is the radiation transmitted? First is the if you look at the one transmission. Okay, so transmission is the amount of radiation passing through the medium when the semi-transparent medium is irradiated. Okay, so transmission, that is amount of radiation passing through a semi-transparent medium when the medium is irradiated. Now the reason why we the reason why we actually specify semi-transparent medium in this case is that in the case of an opaque medium, transmission does not happen. So transmission actually happens only in the case of a semi-transparent medium. Okay, next is absorption, and yeah, okay, we'll come to that. Absorption. Okay, now what is this absorption? So absorption occurs when the radiation actually increases the internal energy. Okay, so if the radiation passes through this thing, passes into the body, and if that is absorbed, if the radiation is absorbed by the body, and then the internal energy of the body is increased, or internal energy of the medium is increased. So absorption occurs when a part of the irradiation, a part of the amount of radiation falling on the object is absorbed by the object, and then the internal energy is increased. Okay, so when radiation or a part of the know what happened. Something went wrong. Okay, now sorry for that, I don't know what happened. Okay, absorption is when a part of the occurs when the radiation, actually a part of the radiation falls on the object and it is absorbed and the internal energy is increased. So if I write that radiation falls on the object and the internal energy is increased. Okay, okay, something happened to the stool. Let me just check what this thing is. We'll continue with this after that. Okay, we shall continue. That was some error that happened. I don't know what happened. Anyway, so absorption is actually a part of the radiation falls on the object. So for radiation, irradiation falls on the object, falls so irradiation falls on the objects. So irradiation falls on the object, then a part is absorbed and then internal energy is increased. Okay, so when the internal energy is increased just because of the radiation falling on this thing, that is called as absorption. And the next is reflection. So if a part of the incident radiation is reflected back, okay, reflected back from the surface, then that is called as reflection. And this reflection actually doesn't make any effect on the medium. Okay, a part of the irradiation falls is reflected and reflected back from the surface. Okay, and it does not make any effect on the medium. Okay, now as I said, it is everything, the transmission or absorption or reflection, everything is just a part of the irradiated ray, or irradiated means the rays that is falling on the surface. Okay, then this part is actually called as the part that is transmitter is called as the transmittivity. Okay, and the part that the fraction that is transmitted is called as transmittivity, and the fraction when a fraction is actually absorbed, then that is called as the absorptivity. That fraction is called as the absorptivity of the medium. And then if a small portion is actually reflected, then that fraction is called as the reflectivity. Okay, so if you take the transmittivity, it is given by transmissivity, that is given by the letter gamma. You can use gamma for that. Fraction of irradiation that is transmitted, that is the fraction of irradiation that is transmitted. Okay, and then the absorptivity is given by alpha, that is fraction of the irradiation that is absorbed. Okay, and next is the reflectivity. So reflectivity is given by rho, fraction of the irradiation that is reflected. Okay, fine. Now when we add, so if you have a radiation, or if you have some rays coming in, a part of the part of the wave should actually reflect, a part of the wave should absorb, and a part of the wave should be transmitted. Okay, if it is a semi transparent medium, the transmission will be there. If it is an opaque medium, there won't be any transmission. So if you add these three parts, you get the irradiation itself. So irradiation is actually split into three, and that one part is transmission, one part is absorption, and the other one is reflection. So you can say that rho plus, for a semi-transparent medium, you can say that rho plus gamma plus alpha equal to 1. Okay, and for an opaque object, you can say that rho plus alpha equal to 1, because gamma, the transmissivity, is actually 0. Opaque objects doesn't transmit anything. Okay, so having explained the reflectivity, transmissivity and absorptivity, we can now go to the radiosity. Okay, the next heat flux, that is the radiosity. Okay, now what is this radiosity? It's given by J watts per meter square. Okay, so it accounts for all the radiant energy leaving the surface. Accounts for all the radiant energy leaving the surface. So whatever amount of energy is actually leaving the surface, that comes under radiosity. Okay, so for a we can just use that for what can I say, we can try to explain this with the help of an opaque object. So for an opaque object, what are the radiations, or what are the part of the irradiation that is leaving the surface? So J is equal to the emission plus G reflection. G reflection is actually rho, right? So this is equal to E plus rho times G, because rho times G is the part of the rho is the reflectivity, and G is the amount of radiosity. Sorry, not radiosity, irradiation, not radiosity, irradiation. Okay, E plus rho G, where rho is the reflectivity and G is the irradiation. So rho into G will give the amount of rays that is reflected from this surface. So that is radiosity for an opaque object, that is J is given by J. Okay, now for a semi-transparent medium, let us see what happens to a semi-transparent medium. In the case of a semi-transparent medium, I'll just clear these. So again we are discussing radiosity, so radiosity. Now for a semi-transparent medium, okay, in this case, if you just I'll explain it with the help of a figure. So for the semi-transparent medium, you have the irradiation coming in, some part of this thing is actually transmitted, right? So if you take let us say it is transmitted through the medium is long enough that it is just transmitted through the medium and it's going forward, and then a small part of the medium, this is reflected. Okay, then there is something that is emitted. Then you can see that in the case of a semi-transparent medium, there will be another so many other rays coming in, right? And those rays will also be transmitted through this. Okay, so in this case, the part of other thermal radiations that is coming in and transmitted through the medium from the below surface, from the other surface, and going out of the upper surface, that should that also should be considered. Okay, in this case. Now next is the net radiation heat flux. Okay, net radiation heat flux. So okay, I just forgot to explain one thing, that is, so in the case of radiosity for a transparent medium, you will have the reflected portion, then whatever is emitted, and the small portion that is transmitted, but that is not actually part of this radiation. The transmitted part is the transmitted part is actually from some other radiation which is coming from bottom or from side or somewhere else. Okay, so that is not part of this one. The part, so it includes the radiosity, but since radiosity is the amount of radiation that is completely coming out of the medium, we should include this also. Okay, now next is the net radiation heat flux. Okay, that you can write it as Q radiated, so that is also watts per meter square, the unit is that one. So that is actually the difference between whatever is going out minus whatever is coming in. Okay, whatever is going out and whatever is coming in, whatever radiation is going out and whatever is coming in, the difference between those two. So this Q radiated can be given by J minus G, where J is the radiosity, that the radiosity which is whatever is going out, G is the irradiation, that is whatever is coming in. So this is equal to, for an opaque object, rho plus E plus rho G minus G. So E plus rho G minus G, that can be written as epsilon sigma Ts raised to 4 minus alpha G, because this alpha G came, we are actually discussing for an opaque object. Now alpha G came from this, that is rho G minus G will be equal to G times rho minus 1, and rho minus 1 we saw, that is alpha plus rho is equal to alpha plus rho will be equal to 1, which gives us rho minus 1 will be equal to negative of alpha, minus 1 equal to minus alpha. Okay, so that is what we have used here. So that is the net radiative heat flux. Okay, now in the next class we will move on to the radiation intensity, and then we will go through solid angle and the amount of radiation and the calculations and all those things.